Welcome to Brain Vision.
In this problem, have the same scenario as in the previous problem, but now the pushing force is going to be 30 degrees below the horizontal. So the worker is pushing downwards. And it still has a normal force, a force due to gravity, and a frictional force counteracting the movement of the crate. And I'm going to break down the pushing force here into its components so we can just work in our two axes of x and y, since that's where the displacement is pointing is along the positive x force. So we're drawing this force diagram with the components of the pushing force. We'll see that this will be equal to the magnitude of the pushing force, Fp, times cosine of 30 degrees. And this vector here is the magnitude of pushing force times the sine of 30 degrees. And label the rest of these here, the normal force, the force due to gravity, and the frictional force. So as we did in the previous problem, we're going to set up two equations applying Newton's second law. And in both of these cases, the sum of the force is going to be 0 because the acceleration in both directions is 0, given by the crate is moving at a constant velocity. So in the x direction, we have Fp cosine of theta, and just to save me some writing, we'll call theta or 30-degree angle, minus the force of friction. And in the y direction, we have the positive y direction, the normal force, and in the negative y direction, we have the gravitational force and the y component of the pushing force. So Fp cosine of theta is equal to the frictional force, which is given by the coefficient of friction, kinetic friction, mu k, times our normal force. And we can figure out what our normal force is here by moving over gravitational and pushing force component to the other side here. So we get Fg plus Fp sine of theta. And then we're going to substitute that into our expression up here. And so I might come down here and do that. So we have Fp cosine of theta is equal to mu k times Fg plus Fp sine of theta. And so in this first part, we're trying to calculate the magnitude of FP here. So I'm going to want to move this expression to the other side and pull out FP and isolate the variable. So we first have FP cosine of theta minus mu k FP sine of theta. Got to remember to distribute that coefficient of friction. And on the other side, I'm going to substitute in for a force of gravity, or mg. So in this case, I can pull out my FP and divide by the expression that's left, which will be cosine of theta minus mu k sine of theta. And we get that FP is equal to mu k mg over cosine of theta minus mu k sine of theta. And now that we have our expression here, all we have to do is plug in the proper values that we were given in the previous problem. So the coefficient of friction was 0.25. The mass of the crate was 30 kilograms. G is 9.8 meters per second squared. And on the denominator of this expression, we have the cosine of 30 degrees minus 0.25 times the sine of 30 degrees. And when I calculate that all out, and again, using only rounding up to two significant figures, I get that the magnitude of the pushing force now has to be 99 newtons as opposed to 74 newtons in order to move this crate as a constant velocity. So this is our answer for part A. And now that we have that, we can start calculating the work for the various forces here. So in part B, it asked for was the work done by this force as it's pushing the crate 4.5 meters. So we're in part B. And what I'll call WP is equal to magnitude the pushing force times the magnitude of our displacement. And the angle between them is now 30 degrees since we're pushing 30 degrees below the horizontal and displacement is along the horizontal. So we have 99 newtons times 4.5 meters times the cosine of 30 degrees. And I have that this is equal to 390 joules. And the next part, it asks us to calculate the work for the frictional force. So due to friction will be equal to, go back here and look at our expression for friction. It's mu k times F of n. And we have our expression for f of n here. So we will use that to substitute into our expression of work here in a moment. And the friction is acting opposite of the displacement, so the angle between the two here is 180 degrees. And we have mu k times Fg plus P sine of theta put some brackets around this, and similar, we just have S times -1. So we can start filling in some things here. Fg is going to be mg. So work due to friction will be 0.25, the coefficient of friction, times 30 kilograms times 9.8 meters per second squared, plus our pushing force, magnitude of that, which was 99 newtons, times the sine of 30 degrees. And all of this is in parentheses, multiplied times 4.5 meters times our -1. And in the end, just like before, we have the work due to friction is equal to negative of the work due to the pushing force. So we have -390 joules. The next part asks us to calculate due to normal force and gravity, and those haven't changed with respect to displacement. Both of them are still at 90 degrees to the direction of the displacement. So there will be a cosine of 90 in their expression for work, which will zero them out. So our force or work due to the normal force and work due to gravitation is 0. And so now we have everything we need to calculate the total work done on this crate. It will be equal to WP plus WFR plus these two works, which are just 0. So we have WP plus WFR, and that is equal to 390 joules minus 390 joules. So just like in the previous problem, we get the total work being done on this crate that's moving at a constant velocity is equal to 0.